Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about shocks and expansion waves. We will look at the conservation equations, that of mass, momentum and energy, and we will try to apply them to normal and oblique shocks. We will also look at the Prandtl-Meyer expansion waves. What we have over here is a control volume. We have drawn a one-dimensional control volume, and it is a rectangular one. It contains a normal shock. It is a stationary normal shock wave that we have inside the control volume. We have marked regions 1 and 2 respectively upstream and downstream of the shock wave, and we have shown that these properties change across the shock. Given the values of these properties upstream of the shock wave, we would like to answer the question that how would the properties figure downstream of the shock wave. This is the area in the sense length times unit depth or unit span, and when we look at this one dimensional control volume and the normal shock that is stationary inside the control volume, we of course recall that we would like to look at the one dimensional continuity, momentum and energy equations and apply it to the control volume. And we would like to take the steady form of the equations and we will apply the Eulerian control volume framework. So, now it is a good time to recall about the Eulerian control volume framework, and you recall that there we use the integral form of the equations, and we do not follow the fluid particles, but rather we fix our view at a particular region of space. Since it is a steady flow, the del t term in the continuity equation that goes to 0, and then we are only left with a flux term. It is a surface integral rho v dot ds, and that should equate to 0. That is the conservation equation. Now, if you try to work out the dot product on the left side of the control volume through which there is an influx of mass, then you see that it is going to work out as rho 1 times u 1 times I dotted with minus a times I. It is because if you look at the inflow region, then the A points in this direction and the u 1 points in this direction, and that is why the term looks like that, and when it is dotted it gives you a minus rho 1 u 1 a. While if you were to look at the outflow, then a I points in this direction and u 2 I points in the same direction. When you dot it, it will give you rho 2 u 2 a. Thereby, there is a difference in sign. When it goes to equating them to 0, we find that this is how it works, and then since a is constant, therefore, it boils down to rho 1 u 1 equal to rho 2 u 2. So, this is the continuity equation for steady one dimensional flow. So, we have got the mass conservation equation. Now, let us look at the momentum conservation equation, and if you recall about the form of that equation, again for the Eulerian control volume approach, you have a time derivative term here, you have a flux term here, you have a stress related term over here and a body force term over here. What we will assume is we will take it as steady, we will neglect any body forces. Additionally, if you recall about the stress term, the sigma ij term, we simplify it only to minus p, taking the normal stress components. We neglect tau ij because we are assuming the flow to be inviscid. Therefore, the tau ij is set to 0, and we also neglect the effect of bulk modulus. Therefore, sigma ij will only contribute the minus p term, and therefore, the equation simplifies to a form like this, where further we have simplified it to the one dimensional control volume, and therefore, the v vector over here would end up only contributing the small u, the x component of v, and the p ds is going to be only having the x component. In the given circumstances, if you were to now calculate it term by term, again you will find that a rho 1 u 1 a with a negative sign, which is what is going to come from the dot product of rho v dot ds, and then multiplied with the corresponding velocity at this station, and again rho v dot ds at this station multiplied with the corresponding velocity u 2, and on the right hand side you have a minus p 1 times a for this particular station, while a p 2 times a for this particular station, because of the orientation of the area vector, and you have a minus sign standing out of the integral, that is what contributes the negative sign here too. Now, if you arrange the terms, the equation comes out to be like this. So, this is the momentum equation for steady one dimensional flow, which basically means that p plus rho u square is conserved across the normal shock. Coming to the energy equation, again the unsteady term is neglected. We are neglecting body forces. We are also considering that the flow is adiabatic. That means you are not providing any q dot into the control volume or extracting any q dot out of the control volume, and therefore, there is no contribution from that term. The only contributing terms are this on the left and the right hand side respectively. So, if you write down the terms now, you find that the small e plus v square by 2 can be written as the capital E term, the way we had written it when we were discussing about the conservation equations, or if you wish, you can continue with the more elaborate description E plus v square by 2, and now try to expand it for the entire control volume. And all this while you may recall that when we take the v dot ds, there is no contribution coming from the upper and lower sides, because there the v and ds are orthogonal to each other, and therefore, when you take a dot product, they contribute a 0 for the upper and lower surfaces. So, the only non-zero contributions come from the left and the right faces of the control volume. So, when you take the dot product here, you end up getting the minus rho 1 u 1 a times the u 1 plus u 1 the e 1 plus u 1 square by 2 within bracket. Here the negative sign is again due to the negative sign produced due to the dotting of v and ds, which has been explained earlier too. For the second contribution coming from the outflow, it is going to be like this, where rho 2 u 2 a are coming from the rho v dot ds, and E2 plus U2 square by 2 is the other term. On the right hand side terms, you have minus P1 U1A and P2 U2A. In all four terms, A is the common one which drops out, and consequently you will see that you are left with P1 U1 plus rho 1 times capital E1 times U1 is equal to P2 U2 plus rho 2 times capital E2 times U2. Divide the left hand side of the above equation by rho 1 U1, the right hand side by rho 2 U2. Remember that by continuity equation they are identical. Then you end up getting a form like this. Further, we know that the collection of terms P times small v plus E is equal to H, where this is specific volume, specific internal energy, pressure, and this is enthalpy. Therefore, the collection of terms here simplifies to enthalpy at station 1. The collection here simplifies to enthalpy at station 2, and therefore, what you see here is conservation of H plus U square by 2 across the normal shock. For calorically perfect gas, that means where Cp and Cv are constant, the following thermodynamic relations can be added to the above three conservation equations. What are they? You have P equal to rho RT, which is the equation of state, where R of course is specific gas constant, and H is equal to Cp times T. You will then find that you now have 5 equations for the 5 unknowns respectively: U2, P2, T2, H2 and rho 2. So, we said that given the values U1, P1, T1, H1 and rho 1, how are we going to calculate these values? So, we have now answered that question in the sense that we have come up with 5 supporting equations which can help us in that direction. And if you algebraically solve these equations, you should be able to get the answer. For thermally perfect and chemically reacting gases, though, you have to solve this system numerically, because the moment Cp, Cv, gamma, these become either dependent on temperature or dependent on the chemical reactions that are occurring, you cannot have a simplified algebraic solution anymore. If you solve these equations, the 5 equations that we are talking about, then you should be able to obtain relations of these forms, which involve Mach number, density, velocity, pressure, temperature across the shock wave, and also you should be able to devise some equation for entropy change across the normal shock. These are very important relations for normal shocks. Try to derive them in your free time. So, this is an equation involving the Mach number in the station 2 as a function of Mach number upstream, and the gamma for calorically perfect gas. Of course, for air we consider gamma to be equal to 1.4. Now, this becomes questionable when we are talking about high temperature reacting gases, typically at hypersonic and hypervelocity conditions, but in the supersonic regime this would be fine. As far as the density ratio is concerned, rho 2 by rho 1 is the same as U1 by U2 by continuity equation. That again can be expressed in terms of the upstream Mach number and the gamma. You have P2 by P1 expressed by this equation, T2 by T1, or that is the same as H2 by H1 for calorically perfect gas, again expressed in terms of M1 and gamma. And here is an equation for the entropy change across the normal shock, where you can easily figure out that there is a definite change in entropy, and it is a rise of entropy which occurs across a normal shock. It is because the stagnation pressure at station 2 is always less than the stagnation pressure at station 1. And there is more that needs to be explored in that respect, which you can start doing in the form of some additional reading. For performing normal shock calculations, the normal shock tables included in the general gas tables are very useful. So, if you refer to a gas table, and you will find part of it is dedicated to the normal shock tables, you will find that for a given M1, you find all these ratios provided in the gas tables: P2 by P1, rho 2 by rho 1, T2 by T1, then the ratio of stagnation pressures P naught 2 and P by P naught 1, again P naught 2 by P1, as well as the downstream Mach number. So, if you read the values from the tables, your calculations become much easier. Let us move on to oblique shock waves. The important thing over here is that instead of the wave standing normal to the incoming flow, thereby the name normal shock, you have an oblique shock which is at an angle other than 90 degrees formed in the flow with respect to the incoming flow, and that particular angle is called as the shock angle beta, where beta is obviously less than 90 degrees. There is also a flow deflection produced in oblique shocks when the flow crosses the shock, and that is called as a deflection angle. You can see it over here. So, the flow bends as it moves across the shock, and when we try to analyze the flow across the shock, we try to look at how the flow has turned and how velocity triangles can be constructed upstream and downstream of the shock. Now, one way you can write the velocities is this way, that the upstream velocity is written as capital V1 arrow representing the vector as u1 times I hat, and the V2 vector represented as u2 I hat plus V2 j hat, where u2 is of course along x direction, V2 along the y direction. But for the time being, we are not going to do it this way. Rather, we are going to draw velocity triangles like the way we have done here. You find that the V1 vector has been resolved into two components, one being tangential to the shock, the other being normal. The tangential one will be called as W, the normal one will be called as U, and therefore, W1 and U1 respectively, because it is upstream, and therefore, it corresponds to region 1. Similarly, downstream of the shock, you will have W2 and U2 respectively. Corresponding to those velocities, you will also have Mach numbers that can be defined. And then you have a control volume drawn over here, which spans across the oblique shock. Part of it is ahead, part of it is behind, and there are surfaces drawn to define that entire control volume. Upstream side, you have B1 and C1 forming part of two streamlines, A1 which is facing the flow V1, downstream of the shock B2 and C2 forming part of streamlines, and A2 facing the flow V2. This way, if we look at the entire geometric features of the flow, we can now look at the conservation equations once again in the Eulerian control volume framework, and assuming that it is steady flow and remembering that U1 and U2 are normal components of the flow and faces A1, A2 are the ones through which the flow moves, and they have identical areas respectively called as A, then the continuity equation will boil down to rho 1 U1 equal to rho 2 U2. B1, C1, B2, C2 phases do not contribute to the mass flux because they form part of the streamlines, and therefore, there is no mass flux moving along those phases. The normal component of the momentum equation again can be worked out in similar lines like the momentum equation we worked out for normal shock. Here the velocity component normal to the oblique shock, remember, is being called as u. It is not to be confused with the x component of velocity, and p ds n would represent the normal component of the p ds term. Now, if we work it out term by term, you will get to a point where the equation looks like this: p plus rho u square is conserved. So, normal component of momentum equation is identical to that of a normal shock wave. The tangential component of the momentum equation again can be written in a similar way. This time the velocity component that we are looking at over here is the tangential component to the oblique shock, and again the p ds term has to be worked out in the tangential sense. When we do that, the rho v dot ds occurs only through the faces A1 and A2. This dot product has to be multiplied with the corresponding value of w to obtain the left hand side of the equation. That is rather straightforward. For the right hand side term, pressure force acting on faces B1 and C1 are equal and opposite. Therefore, the forces on these faces are going to be opposite. Therefore, they cancel each other. The same applies to the cancellation of pressure force acting on B2 and C2. Therefore, these would cancel each other, and remember that they are working normal to each one of those faces, and they are equal in magnitude, but they are opposite in sense. The pressure forces acting on faces A1 and A2 are in the normal direction, and hence they do not contribute to the tangential pressure force. While in this equation we are trying to figure out the tangential part of the pressure force only. Therefore, the right hand side overall is going to be 0. Therefore, no contribution in the tangential direction coming from the p ds term at all. Hence, the tangential component of momentum equation yields a form like this, which simplifies to W1 equal to W2. So, this equation states that the tangential component of the flow velocity is constant across an oblique shock. There is no jump in that value. Coming to the energy equation, we recall after the simplifications the energy equation looked like this. Even for the normal shock we had discussed about the simplifications. Only the faces A1 and A2, they would yield non-zero values of the V or ds term. On the other faces B1, C1, B2 and C2, the flow is tangential to the faces. Therefore, V dot ds is 0. The energy equation would therefore end up forming terms of this kind, and finally, it gives you an equation in this form, where H1 plus V1 square by 2 is conserved, or rather H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, which can be called as H naught, and this is what is conserved across the shock. However, we would like to know the relation in terms of the small u's, and therefore, we need to do a little more work. V1 square can be written like this, V2 square like this, and since W1 is equal to W2, which we have already shown through the tangential component of the momentum equation, therefore, we can write this equation, and this equation is identical to the energy conservation equation we had worked out for a normal shock. We therefore see that changes across an oblique shock are governed only by the component normal to the wave. Additionally, the continuity, momentum and energy equations turn out to be identical to a normal shock wave when considering the normal component of the velocity to the oblique shock. The normal component of the upstream Mach number can be expressed like this, which very easily comes from the geometry that you see over here. M n1 is equal to m1 sin beta. Similarly, normal component of the downstream Mach number mn2 can be expressed as m2 sine beta minus theta. Based on the above two normal Mach number components, we can write these relations again. Involving only the normal components, these equations are written, which are basically normal shock relations being fitted into an oblique shock scenario. And of course, all the way we are assuming a calorically perfect gas behavior. We also have an expression for rho 2 by rho 1, P 2 by P 1, T 2 by T 1 and so on. And remember that for a normal shock, theta happens to be 0 degree, the beta happens to be 90 degree. From the velocity triangles, we can write tan beta is u 1 by w 1, tan beta minus theta is u 2 by w 2, and since w 1 is equal to w 2 and by continuity equation rho 1 u 1 is rho 2 u 2, you can come up with a relation like this, which after some more calculations reduces to a form like this, where you have a relation connecting theta, beta and m, and this is called as the theta beta m relation for oblique shock waves. When m is a parameter and you try to plot theta versus beta, these are the curves representing the different Mach numbers. So, as you see that the inner ones are for lower Mach numbers, the outer ones are for the larger Mach numbers, and then m 1 as it tends to a very large infinite value, that would basically define the furthest extent of the curves that you see over here. And as discussed earlier, you have weak shock and strong shock solutions corresponding to small and large values of beta corresponding to a specific value of theta for a given Mach number. And then you always have a theta max corresponding to a given Mach number. So, this is the theta max for Mach 10, this is the theta max for Mach 5, like the way it has been sketched approximately in this plot. So, this plot is nothing but a graphical representation of the theta beta m relation. When you go beyond theta max, you have a situation like this. When you are well within the theta max, you have a situation like this. So, this is a straight oblique shock that has been formed, while this is a detached curved shock that has been formed because your theta has exceeded theta max. This is for flow past a wedge, while you could imagine that if there was a compression corner on a flat wall, then the similar attached or detached shocks would have looked like this, the way we have sketched over here. We will discuss about the Prandtl-Meyer expansion fan. Unlike the flow through a normal and oblique shock where entropy rises, flow through a Prandtl-Meyer expansion fan is isentropic, and you find that the flow is moving past a corner and expanding through the fan. There is a forward Mach line and a rearward Mach line indicating the beginning and end of the continuous expansion fan, and these angles mu 1 and mu 2 are defined in terms of the upstream and the downstream Mach numbers which occur across the fan. This is a small geometric representation of how things work out across the fan, and you find that this is the upstream velocity vector, this is the downstream velocity vector for a very small deflection angle d theta, and the small velocity change that has happened can be indicated through this length scale. This length scale is the same as v, and the angles have been indicated over here in the triangle. This is the Mach wave corresponding to the expansion fan that we have over here, formed due to the small deflection angle d theta. There is an infinitesimal change across an infinitesimally weak wave. From the law of sines, it can be written that V plus dV by V is given by sine of pi by 2 plus mu by sine of pi by 2 minus mu minus d theta. We recall that Mach waves are produced when you have a very weak disturbance in the flow field propagating through the flow field. It is more like a beeper or a small sound source which is moving through the flow field, and it is moving at a velocity v, and the sonic velocity corresponding to the temperature, the static temperature of the gas is A, and therefore, you would have different scenarios if it is moving at a subsonic velocity and a supersonic one. We find that in the subsonic case, the disturbance patterns always lie well ahead of the disturbance source, while in a supersonic case, where the source of the disturbance is moving at a velocity greater than the sonic speed, the disturbances kind of coalesce into weak disturbance fronts, which we call as Mach waves, and they are slanted to the flow, and this angle at which they are slanted is given by that angle mu, and we can show from the geometry that the sine of the angle mu is given by A times t by V times t, which is nothing but 1 by m, based on the distance of propagation of the sonic waves versus the distance of propagation of the disturbance itself. So, this is basically the background of obtaining the value of mu, and coming from the diagram that we saw in the previous slide, if we do some more calculations, we can show that we can integrate that relation d theta equal to under root m square minus 1 into dV by V, and we can finally come to a function which we call as the Prandtl-Meyer function given by this relation. There is a little bit more we would like to discuss, but we will try to extend that discussion to the next lecture. In this lecture, we discussed about normal shock, oblique shock, and quite a bit of Prandtl-Meyer expansion fan. The conservation equations were applied and the special forms were obtained. Thank you.